Hi, this is Sam Proctor from the Software Solutions Division with your SEI Cyber Minute. Modern systems are so deeply interconnected that the impacts of component and configuration choices can be difficult to anticipate at design time. This is true even of critical systems, that is, those systems whose failure can lead to unacceptable financial losses, injuries, or even death. Increasingly, these systems are built from components selected from a large number of different vendors. As these systems grow more complex, developers cannot test all the options thoroughly enough to know which ones optimize performance or even comply with system requirements. Consequently, uninformed choices can lead to rework and higher sustainment cost, but these problems can be avoided. Here at the Software Engineering Institute, we have created a new tool prototype that automatically explores a system's design trade space, that is, its possible combinations of system software, hardware, and configuration options. This prototype, which combines previous work here at the SEI with software from Penn State University, enables system designers to rapidly evaluate design options. This rapid evaluation supports a new design paradigm called design by shopping. Much like traditional shopping, it begins with a broad search of candidates that potentially meet some need. Individual candidates, in this case system architectures, are automatically evaluated according to their quality attributes like cost, performance, weight, and power consumption. If none of the candidates are satisfactory, more can be generated or the search can be refined. This work builds on the SEI's existing work in system architecture modeling with the Architecture Analysis and Design Language, or AADL, which enables the creation of the very detailed models of a system's architecture used in this project. System development costs are rising at an unsustainable rate. Much of this rise is driven by software, and designers are scrambling to contain those costs. SEI's work in system architecture modeling addresses this need head-on by modeling software, hardware, and the bindings between the two. Using this existing modeling technology with a trade space explorer like Penn State's has the potential to produce higher quality system architectures in less time. Thanks for watching this SEI Cyber Minute. For more information, please visit our website or send me an email at info@sei.cmu.edu.
Next, we have an overview of AADL and Toolsets to support the engineering of safety critical systems by Jerome, Hugues and John Hudak. Jerome is a senior researcher at the Software Engineering Institute on the Assuring Cyber Physical Systems team. And John is a senior member of the technical staff here at the SEI. His interests include dependable real-time systems, computer hardware, and software architecture, model-based verification, and control engineering. Here is Jerome and John with their talk.
Hi, and welcome to our talk, an overview of AADL and its toolset to support the engineering of safety critical systems. In this talk, we'll provide a short introduction to AADL as a language, but also detail how this technology can be applied to fully engineer, validate, and deploy a cyber physical system. First, let us expose our context. Our goal within the ACI is to make critical systems safer and more secure. Because we know that traditional methods are no longer good enough for the critical systems we need to build, the ACI is working to bring what we have learned through research and prototyping of those capabilities to the field quickly, which is the reason why we are here today, to learn more about the tools and applications that enable the use of AADL and the use of ACVIP in real applications. We, as a team, build our own expertise, working on model-based engineering. The MBA team within the SEI improves state-of-the-art and influences the state of practice to field software faster in confidence. Our vision is to leverage models, first to create the best design that will hold up over time as the system is evolving. Second, to test the design in all its dimensions, functional, timing, performance, security or safety, using state-of-the-art technologies as early as possible, even before the software is actually written. All of that is made possible by first defining a high-level modeling language that will combine hardware and software processes, but also a language that will allow to reason on the architecture core quality attributes. This set of assets is what the SEI has been developing over the last 20 years. First, the SAE Architecture Analysis Design Language, or AADL. AADL is a domain-specific modeling language for modeling safety-critical systems, merging software and hardware concerns and a large set of properties to configure a system. This language is supported by many tools. This includes the SCI AADL toolset that supports model editing and analysis capabilities. As part of SCI FFRDC mission, those technologies are increasing in maturity through multiple case studies for the US Army and for its partners. So, the main idea of AADL is that you can analyze your system before you even write a single line of code. Indeed, AADL allows you to test your design and to validate some of the key attributes. For instance, what are the performance of the system? Do you validate key metrics in terms of end-to-end latency, in terms of respect of deadlines? Do you validate safety or cybersecurity objectives? All of that can be assessed thanks to AADL exhaustive suite of tools capabilities. Therefore, we at the SCI believe that the AADL has a potential to change the way software is being developed. Today, we will cover two aspects of AADL. First, we will discuss model-based engineering for software-intensive systems using AADL and introduce the key aspects of the language. I leave the room to my colleague John Hudak to present this facet of AADL.
Thank you, Jerome. This part of the talk will cover 4 areas: challenges of embedded systems as motivation for our architecture-centric approach, characteristics of model-based systems engineering, followed by an overview of the AADL standard, and wrapping up with an overview of tooling that supports AADL. So we rely on software for safe system operation. Shown on this slide are examples of accidents that have happened due to software errors. Some years ago, there was a problem with the Boeing 787 in which the APU would shut down after a period of time, resulting in loss of power to the aircraft control systems. Without power, the control surfaces and related instrumentation would not be able to operate, and the plane would be uncontrollable. A more recent problem was with the Boeing 737 MAX 8. The aircraft incorporated a larger engine that changed the aircraft flight dynamics, making it unstable in parts of the flight envelope. The job of fixing the aircraft stability problem was given to the software embodied in the MCAS. Part of the problem was traced to badly designed software of the MCAS, but also the integration of the software into the existing flight controls. When engaged, it would counteract the commands from the pilot based on erroneous data. Both of these aircraft problems were traced to software faults. These design faults made it through all types of testing and certification, but were never caught. The issue that we want to address is to ensure that these types of software faults are caught early in the development of the system so that they do not appear during later phases of integration testing or worse into the fielded systems. To do that, we need to identify the origins of the faults and the reason for their occurrence. So what are the challenges in increasing the quality of embedded systems? Research based on looking at historical data of similar software-intensive systems have shown that 80% of the software issues are discovered post-unit test. Post-unit test includes integration, system and acceptance testing, through to deployment of the system in the field. The approach that the SCI has been advocating is the development of strategies for early discovery of faults using an architecture-centric approach to system development. This is accomplished through modeling of the system architecture and its architecturally significant attributes. This approach consists of the ability to precisely model a system architecture and to virtually integrate the characteristics of new components as the system scales. The approach also embodies the ability to perform analysis incrementally throughout the development lifecycle. The approach we have been developing is based on formal modeling language and related practices, which we will introduce later in this talk. To address faults early in a development lifecycle, we must know where they occur. On this chart, we show the V software development lifecycle, which you have probably seen many times before. It has been shown that as much as 70% of the requirement and system interaction faults are introduced during the early part of the system development process, where the cost of fixing them would only be 1x. However, only 3.5% of these faults are detected early, which means that roughly 80% of the errors are discovered late in integration and testing. And the cost to repair them increases significantly, ranging from 20 to 100x. So the architecture-centric development strategy is to place more emphasis on architecture design and analysis early in the development lifecycle to detect and mitigate faults as they are introduced. By doing this, we will realize a significant amount of rework. As an example, a $10K correction effort in the architecture design phase could potentially save upwards of $3 million because backtracking and correction of faults are minimized. So now that we know where in the development process the faults occur, we must understand the types of faults that show up and how they manifest themselves in safety critical systems. Consider that we have a system engineer who defines the system under control and a software engineer and the control engineer who develops the control software. During the design of the control system, the control engineer must understand interfaces to the system under control. That includes the type and range of data and latency, for example. Additionally, user input can give rise to system hazards, also needs to be considered. So what do system level fault failures still exist despite our best practices? The reason is that the control software coexists with application software whose operation and coordination is orchestrated by a runtime architecture, which is housed on a computing platform. There are interactions between these elements, as shown on the slide, that point to the architectural properties that must be correctly specified and evaluated within the system. For example, between the control system and the application software, the data types and their units must be consistent. The runtime architecture must coordinate the execution of the control system along with the application software, which gives rise to potential concurrency and communication issues. The runtime architecture must ensure that process data from the system under control is presented to the control system in a timely manner to meet the sampling frequency that is specified by the control laws. To help ensure determinism, we must precisely capture the structure of the system and the semantics of the operation of these elements. The architecture description must be able to capture the architecturally significant properties that come out of the design by all engineers, the control, software, and hardware engineers. Furthermore, the architecture must be analyzable for a number of system properties. The architectural model must be able to support analysis from many different views of the system. These include cybersecurity, resource consumption, performance, data quality, safety, and reliability. Analytical views are generated from the same model source. This establishes consistency across all analysis results. It also allows for understanding the impact of a system change that affects multiple system properties. This is illustrated in this example. Suppose that the cybersecurity area, we change the encryption algorithm from 128 to 256 bits. This can cause a higher CPU demand, resulting in a change in latency, which can result in sampled event being missed. The resultant jitter can change the temporal correctness of data, which in turn can cause a weapons release protocol to lock up or a braking system to malfunction, presenting a new safety hazard. Such issues can be very expensive to find and deadly in effect, yet seemingly unrelated to the encryption change that we have shown. What this example shows is that the single change in one area can impact multiple system quality attributes. The designs to address quality attribute requirements are driven by experts in the field, such as safety and security. They need to communicate with each other to understand how their design changes impacts one another's area. Having a formal model removes any ambiguity with respect to cross-domain dependencies. There is one model that contains all the domain-related properties and supports the multi-domain analysis. This framework promotes the capability of continuous incremental verification of the system, and its architectural model is modified and refined to greater detail. This provides immediate insight into the impact of changes and refinements and reduces the late discovery of faults during system integration. Now we'll talk a little bit about model-based engineering and AADL. Let us look at model-based systems engineering and software engineering in a broader context to better understand the needs as one goes from a concept of a system through to code implementations. Model-based software engineering should enable the software development effort by eliciting stakeholder needs and constraints and developing an understanding of these requirements with the affected stakeholders before committing to them. We want the models to capture system elements through new designs, reverse engineering, or COTS. We also want to capture the component interfaces and the internals, which will eventually be part of system architecture. We can then use the architecture to look at software deployment and potential configuration trade-offs. We want the ability to apply analytical frameworks to assess the model's compliance to objectives such as syntactic conformance to guidelines, for example, an airworthiness certification document. On step 4, we eventually want to generate code from the architectural models. For example, MATLAB or Simulink have the ability to translate their functional models into C code. In order to generate code for an architectural model, we must precisely express the characteristics of the runtime system. In some cases, modeling can be viewed as the new programming paradigm. Understanding the architecture enables us to reason about system-level properties which code-only solutions cannot address. The quote from Nkosi offers significant insight into the attributes of a comprehensive model-based engineering approach. Model-based systems engineering approach is the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities, beginning at the conceptual design phase and continuing through development to the later life cycle phases. SysML captures the relationships among system functions, requirements, developers, and users only during the early development of a system. Obviously, other modeling notations are necessary to model such things as component and configuration of hardware systems, architecture of the software, behavior semantics, and the deployment of the software onto the execution platforms. These notations would enable analysis of system quality attributes, including safety, security, and performance. These notations would also allow analysis to assess the impact of design changes in one area with respect to the other, such as security on performance. As part of the vision to achieve comprehensive model-based engineering approach, the SEI has been a major contributor to the development of AADL standard that targets modeling of and analysis of embedded real-time systems. Embedded systems are composed of physical systems such as the aircraft or a car, the software system, which is the software design and the runtime architecture, and the computing system, which basically is the hardware architecture and the operating system. The software system interfaces to the physical system through sensors and actuators. The software system notionally is connected to and interacts with the physical system by sending and receiving commands and control. The software system is deployed onto the computing system, effectively using it as a proxy to talk to the physical system. The AADL standard is able to capture and represent the interfaces of an embedded system by its ability to abstract model physical elements and the hardware and the software. So if we unfold these concepts, we come to the realization that model-based system engineering is more than SysML and AADL. It is the aggregation of a number of standards that contribute to system development, which is composed of the physical system, the embedded system, and the computing hardware. So where does AADL standard fit in, given a large set of applicable standards, tools, languages, and analysis techniques within the context of the development phases of the system? As part of the overall development process, we see that we can use a number of existing tools and standards. Many of these that are shown on the screen you are probably familiar with. The top of the slide contains the various development steps, starting with mission system requirements, subsystem architecture, component design and implementation, and system integration and qualification. We have mapped existing tools and languages as they apply to each part of the development process. Looking at the mission system requirements phase, we see such tools as DODAF, and further into the life cycle, we have SysML. We can look at the tools that contribute to system engineering activities in the computing hardware and software and physical systems as well. In the computer hardware, we see VHDL and Verilog. In the embedded systems area, we see FACE supporting system architecture and development languages such as C and Python in the component implementation area. In physical systems, we see MathWorks and Modelica used in subsystem and architecture phase. If you go a little further, you will see that AADL fills several gaps. AADL is a conceptual overlap with SysML, allowing AADL to capture the physical and functional aspects expressed in SysML. AADL is used to model the embedded system architecture, which provides for the analysis and blueprint for the construction of downstream code artifacts. By employing AADL early in the development lifecycle, one can virtually integrate characteristics of new components, and we can evaluate their impact in the overall embedded system architecture. So now we'll talk a little bit about the AADL language. The AADL is an SAE International Aerospace standard. The current version is 2.2. The focus of AADL is on embedded software systems modeling, analysis, and generation. It is a strongly typed language with well-defined semantics for execution of threads, processes, on partitions, and processor, being able to represent sampled and queued communication, has the concept of modes and end-to-end flows. There is a textual and graphical notation. There also is an XML, XMI interface to ease processing and integration to third-party tools. Currently, AADL version 3 is in the development process. As a pointer to find out more about AADL, there is a link on this slide. There is ongoing work to further align AADL and SysML in a common workflow by the SCI, Aventium Labs, and ANSYS. In addition to the core modeling language, there are standard annex extensions. For example, the air modeling language that addresses safety and reliability analysis, ARINC 653 extensions for modeling partitioned architectures, specifically ARINC 653, AADL runtime system for code generation, and the FACE annex, which supports the FACE to AADL translator later. And annexes that are in progress are the cybersecurity annex, and future annexes include the requirements definition and assurance annex. Some of these are embodied currently in the SEI ASATE toolset. So, what are the AADL components? They fall into two categories: the application components and the execution platform. The words in bold are the textual AADL keywords, and the icons are the graphical representation. In the application components category, we have system, where system components represent a collection of systems that can be organized in a hierarchical fashion. A process represents a protected address space that can contain threads and data. A thread is a schedulable unit of concurrent execution. Thread groups are used for organizing threads with the same execution properties. Data allows us to model shareable data. Subprogram is a callable unit of sequential code. In the execution platform category, we can represent processor and virtual processor, which provides thread scheduling and execution services. You can represent memory, which provides storage for data and source code. Bus and virtual bus allows for the physical connectivity between execution components. Devices allow one to model the interface to external environments, such as sensors and actuators. So what does AADL look like? The core language is based on semi-formal semantics that are analyzable quantitatively, structurally, and behaviorally. The language format is described in BNF in the standard, along with usage and legality rules. The language describes a static implementation of the embedded hardware and software architectural components and their associated properties. On the right, we see the graphical component connector view of a system. Parts of the components contain the interface descriptions that include data and behavior. The connections between the systems have precise semantics with respect to communications and structural legality. Here we see the textual version of the AADL language. Keywords are bolded. Components have predefined subclause formats that are specific to a component type and a different one for its component implementation. Within ASATE, the SEI development environment, edits in either representation are reflected in the other representation. Annexes are extensions to the core language that contain a set of keywords and property descriptions that allow the model to be annotated with properties for additional analysis, such as hazard identification, error types and flows, and behavioral descriptions. Looking at a more detailed example, we see on this slide a textual and graphical representation. On the left-hand side, we have a system declaration named car system. That is the top-level container that will hold all of our architectural components. The data component, my brake data, is an abstraction declaration for some brake data. The device component abstractly models the brake pedal, which contains an interface feature output port through which my brake data is presented. The system braking system is, at this point, an abstract representation. It has an interface feature named in-data port that specifies the data that it transmits, named my brake data. As the model is refined, it may contain software components, thread components, and additional hardware components, depending upon what analysis needs need to be supported by the model. The system implementation named carsystem.impl contains the subcomponents that make up the car system, along with the connections from the brake pedal to the braking system. The graphical implementation is on the right-hand side. This abstract representation contains the architectural structure and data from which some initial analysis can already be done. The detailed information is added as the design continues. The analysis will incorporate the properties and structure of the new components. Even at this level, some verification can be done. For example, ensuring that the interface descriptions are consistent and that the desired communication direction is represented as per the requirements. If a thread model with flows and with threads is added, the latency analysis would include the effects of thread execution and communication sequences. Building from the concepts of modeling runtime characteristics, this slide shows an example of increasing model fidelity. This model is of a producer-consumer system that shows different levels of model detail. At the top, producer and consumer processes are modeled, each containing a thread with a specified period of 20 milliseconds. Data is communicated via the connection between the two. If the thread specifies an execution time, the latency analysis could be performed to see if specified aggregate component latency meets a system latency. More detailed modeling can be done to include memory that would contain the processes. Memory utilization analysis could be run to see how specified memory budgets compared to a memory usage requirement. Modeling the processor adds another level of detail in that the processes and threads can be bound to a CPU. If a MIPS capacity property is added to the CPU, a processor utilization analysis could be run to see if the bound thread loads exceed the MIPS capacity of the processor. Finally, the bus component with communication latency is added between the two CPUs. By binding the connection at the top between the processors to the bus, the latency analysis would now take into account the communication latency of the bus. This illustrates how architectural models can be refined. The analysis uses the properties associated with each of the refined components. Modeling in the small. The purpose of this slide is to convey the concept that AADL contains modeling components to precisely model the runtime architecture. Each of the component types, highlighted in bold, have precise semantics and properties that allow specifications of that component, ranging from a very abstract model to a detailed one. At the lowest level, processes and threads can be modeled. As systems evolve to have additional threads, for example, system-wide concepts of data and event flows, end-to-end flows, and shared data accesses can be specified and analyzed. Modeling in a large. System-wide concepts can be modeled and analyzed in AADL. The AADL keyword that enables this are shown in bold. For example, the use of mode and mode transitions can be annotated to components to indicate system-wide modal behavior. Many systems have operational modes, for example, manual, automatic, and semi-automatic. Components that are specified as being active in certain modes are considered in various analysis. For example, a set of threads may be active in a particular mode, and a different set of threads may be active in another mode. One can evaluate processor utilization for each mode state. Modes are useful to specify the semantics of fault-tolerant schemes that include what components constitute a primary and backup system. Furthermore, the model can represent the semantics of switching between primary and the backup, and under what conditions the repaired primary system can be reactivated. AADL also supports large-scale system development by using the refined concept, which enables one to model family variants to add new interfaces or properties to the components. 1- and 2-dimensional component arrays facilitate modeling of family of systems. The use of packages facilitates modeling model organization. Additionally, the ability to extend model components by adding features or specifying extended configurations is useful for modeling a family of systems. In the next few slides, we'll talk a little bit about AADL tooling. AADL capabilities. The concepts in AADL provide a good foundation on which a number of analysis technologies in many different application areas have been developed and applied. This is evidenced by over 1,600 plus academic publications with many different use cases, ranging from requirements elicitation, capture, and verification through derivation of code. The leveraging of AADL has occurred through plugins developed in ASATE, exporting the models to third-party analysis tools, as well as incorporating AADL model development into existing tools. This list is a sampling of analysis technologies and their associated formalisms, as well as their resultant tools or analysis environments. Some examples include AADL and development tool chain, taking SysML models and translating them to AADL components, referencing the use of Simulink models from AADL and incorporating properties from those Simulink results into AADL. AADL has been incorporated into SCADE Suite from ANSYS, leveraging the architecture representation to feed a set of their analysis tools within the SCADE Suite. In support of architectural patterns, some examples include the ability to represent multiple independent levels of security, or MILS, approach to high assurance systems. The concept of partitioned architectures is supported, such as ARINC 653 specification that specifies time and space partitioning of a system. In the area of fault analysis, the error modeling annex provides concepts for describing error types and flows that can be supported by mapping to various notations, such as stochastic Petri nets, supporting the analysis into such tools such as PRISM. Many of the notations and analysis techniques are gradually finding their way into real-world industrial projects. This slide contains a subset of tools that have been developed to supporting modeling and analysis using AADL. ASATE is the open source AADL tool environment, which is an integrated development environment developed and maintained by the SCI. The current version is 2.9 and fully supports the current version of AADL, and also has a textual and graphical representation. It has a suite of analysis tools integrated into it, such as latency, processor memory utilization, weight, power, and data security, to name a few. Updates and bug fixes are done on a quarterly basis. ASATE serves a couple of purposes: as a modeling and analysis environment for industry, and as an academic research platform for prototyping new language constructs and analysis tools. KMET is a tool suite developed and maintained by Adventium Labs and has a large number of analysis tools that directly integrate into the ASATE distribution. Some of the more noteworthy tools are the MILS plugin and a framework for analysis and schedulability, timing, and resources called FastStar. The links here will get you to their website. I'll just briefly mention SCADE Architect, and finally, AADL Inspector from Alidus. More information can be found at the links on these slides. In summary, this brief overview shows that our work in model-based system engineering is fulfilling the concepts of the NCOSE definition. We have been continuing the development of AADL, the annexes, the related technologies such as architecture-centric virtual integration. There are benefits of this technology for model-based systems engineering as a whole. We have shown some of these benefits, for example, the conceptual overlap and transition from SysML-based efforts into runtime representations. The architecture-centric approach supports analysis to detect and minimize faults early in the design lifecycle. We represent the AADL components and show that they can be modeled at different levels of the abstraction, but also different aspects of the system, and that they can be combined to capture the entire system at different levels of detail. The key concept is that the formalized models directly support automated analysis in a number of domains that we have talked about: performance, safety, security, and behavior. A benefit of AADL as a standard is a common modeling notation across organizations. This allows for having a single architectural model from which different views of the system can be portrayed. Finally, the common model also supports the concept of virtual integration that allows for the interchange and integration of architectural models. Now I'll turn it back over to Jerome.
Now that we have seen what AADL is about and the promise made by AADL, let us go into more detail and review AADL in practice. How can we use it? And so here, at the last step, what we propose is a simple promenade in AADL. And for that, we'll assume that we plan at implementing our own UAV control logic. And for that, sorry, we will use the Crazy Fly micro UAV as an example. Let us imagine that we have just one high-level requirement, which is to pilot this UAV using your mobile phone as a remote control. What we want is to capture the functional chain and refine it down to a logical and physical chain. You want to perform verification, validation, and ultimately simulation or cogeneration of your system. And for that, we'll use AADL as a backbone for all models. If we start thinking of it, you may come with the mental picture that you see on the right. A little bit of SysML, a little bit of AADL, Simulink or C-code, and ultimately this UAV. Now let us see how we can organize our project. First of all, what is the bit craze and why did we choose it? Well, we chose it because it's open source and open hardware, and also because it is representative of a canonical UAV architecture. Two CPUs, multiple sensors, multiple network interfaces, and software elements. The software in the current version is basically C code and a FreeRTOS operating system. Because the Crazy Fly is open source and open hardware, we can revisit it and look at all the blueprints. The Crazy Fly architecture with the two microcontrollers, the sensors, energy, power, antenna, etc. We can see also the flow between sensors, processing units like the sensor fusions or the controllers, data coming from the pilot, the commander, and ultimately actuation on the motors. We can see also, combined to those to this data flow in the system, what is a sensitive control loop that we have to implement with a controller in attitude, a controller in position for a system that will receive data from the sensors, perform some computation, and ultimately actuate on the system. Now let us play this exercise of re-engineering the system using model-based. So for that, if we follow a basic process, we will go from requirements to architecture, from architecture to detailed design, and to some extent to the application code. And through the selection of the architecture, you will select also a middleware operating system to execute your system. Because we are strongly believing into the separation between runtime and functional elements, what we want is to separate those two between the runtime architecture that will support the execution of the functional architecture made of simpler blocks. What we want basically is to mitigate and isolate the functional code. The functional code is basic computations, basic data processing, but it has to be organized in such a way, it has to be scheduled in such a way that ultimately it will deliver the functionalities expected. For those elements, the state of practice is already well established. We can use UML, we can use SDL, SCADE, Simulink, whatever, to engineer those functional code. What we want to concentrate on is on the architectural models, because the architecture will be in charge of delivering precisely the right functionality in the right time, executing the right function, and moving the data to the right place in the system. And so for that, what we want is generating or configuring the middleware from the architecture, make it possible to use formal methods so that we can analyze the system in a more precise way, but also connects to MBSC, connects to CSML that we discuss, and as a long term, have a certification objective for that process. How can we use AADL for that? So, first aspect, as we discussed, is that we want to use AADL for capturing the architectural system, and for that, we'll simply unfold a regular model-based engineering process. We'll start building our various functions as a collection of abstract components, and we'll organize it in such a way that each high-level function of the system, accelo collecting data about the acceleration systems, the pilot, the gyro, etc., can be bound together. And the way we will connect them is by defining a functional chain that will faithfully reproduce the flow of data from the sensors to the fusion controller and motors. And so in this first step, we are simply reflecting the abstract diagrams that are coming from the Crazy Fly documentation. The second stage is to apply exactly the same strategy for the hardware platform, for which we can define a library of components for the various devices, for the sensors, the actuations, communication buses, I2C, PWM, and ASPI, and the definition of our various processors. And because we're using AADL, we know that each of those elements will come with their own graphical notation, will be also subject to specific legality rules, like for instance the fact that a device can be connected to a bus, like a processor can be connected similarly to some bus, so that you can have data exchange between those. Now that we have defined that, we can go a little bit further and say, okay, we have the hardware platform, and now what we need is also to think about the software platform, for which we will define processes, firmware that will be bound to the same processor, and those software processes will define binding interfaces so that you can allocate a process to a processor. At this stage, what we have defined is the complete physical platform of our system, and what we can do is perform an allocation of the functional models to the physical models that we have just defined. Those separation is actually quite familiar and clearly illustrate the domain usage of AADL. The functional elements can be put in direct relationship with the CSML language that will have defined similarly the same functions with additional requirements, additional use cases, additional high-level behaviors that will have to be refined. Enter AADL that will map this functional to a more precise architectural description, supporting the system so that ultimately you can perform analysis, like for instance scheduling analysis using the Cheddar toolchain, but also code generation with this idea that this architecture can be turned into a particular instance of an operating system. Now that we have modeled our platform, we can go and perform one step of analysis, which is to say, we have defined our system, but what about the conciseness or preciseness of our system? For that, we can also extend AADL and define a language so that we can perform project-specific analysis. Like for instance, in the case of the UAV, what if you want to enforce specific architecturing style for a system? ARINC 653, security, deterministic real-time system following the Ravenscar profile. Ultimately, the idea is to define a set of properties that you want to evaluate on your architectures, a collection of predicates. And for that, we are using Resolute, which is a plugin made by Collins that Darren Koffer presented before. The main idea of Resolute is to leverage this annex capability that we have in AADL so as to attach a specific claim that we want to prove on a system instance. Like for instance, Ravenscar sys is following the rule of the Ravenscar profile. And the Ravenscar profile is defined following the pattern that you see below. It is a set of predicates that say that the system has such and such property, is following such and such guidelines, so that ultimately you can check that, yes, your system is conformant with a specific modeling style. This aspect of architectural pattern enforcement is important because it is these steps that will enable all the following ones. The first one that we can think about, even though it may not be the most logical order, is code generation and middleware. The idea is to consider that through AADL, we are capturing tasks, we are capturing queues, buffers, protocols. And what we can do is simply generate a middleware stack on top of a runtime or real-time operating system. And so if we take this example of a system made by with the European Space Agency, we will have user code that are attached to specific threads within your system. And what we will do is we'll define a container around it that will support the interaction with ports, message queues that are the basic mechanism to exchange data. Because we know in the system what are the various connections, we can also configure a middleware whose role will be to dispatch requests as they are sent by producer and received and processed by consumers. Because we know the communication buses, because we know the operating system, what we can do is rely on a particular implementation of the AADL runtime services that will be specific to the target environment. By combining all those elements, actually a significant part of this middleware is generated directly from the model. And a smaller part is what we call a runtime for AADL. This strategy is the one that we have developed for the Ocarina toolset, which is one of the many code generation tools that you may see around AADL, like for instance Ramses from Telecom Paris Tech, Hammer from Kansas State. They all follow the same idea of generating code from a set of AADL models and demonstrating that the quality of the code is relevant for targeting high integrity safety critical systems. Now that we have performed code generation, now that we know that we can actually map an AADL model to code, we may think about a validation and verification strategy. The first aspect is, again, to start from what is the least reasonable to say, okay, what about the code that we can generate from AADL model? It is important to consider code first, because if we cannot, we will end up with an AADL model for which we cannot generate an implementation. Therefore, our strategy has always been first to demonstrate that we can implement something out of an AADL model. And so recently, what we have demonstrated is that the code we generate is not only compatible with high integrity profiles for safety critical systems, but also the code itself can be demonstrated to be correct by construction. And so what we have done is we have used Spark 2014 ADA extensions to annotate our AADL runtime and demonstrate that our generated code is correct by construction, which means free of any form of runtime errors, but also is valid with respect to specific functional contracts that specify the behavior of the system. Now that we have demonstrated that, yes, we can actually generate an implementation out of an AADL model, we can go back and say, what about a validation and verification strategy at model level? Our belief is that prior to code generation, we have to ensure that the model is safe. And for that, we are using the AADL static and behavioral semantics. Of course, we have to carefully define what is our VNV strategy. And for that, we have to use the right property, we have to define the right property and use the right tool. We can, for instance, consider that some properties are specific to the architectural pattern that we are using. For instance, absence of deadlock is an interesting property of Ravenscar profile. We don't need a model checker for that. That you are carefully following specific modeling patterns is something that you can check with Resolute or at code level with Spark. Then you can ask yourself, what about flow latency, scheduling analysis, or safety analysis? And for that, actually, we will go back to our model. And you may remember this is a functional chain of our system. We can isolate, using the flow concept of AADL, specific paths in the architecture so as to evaluate the path from the output of the accelerometer to the motor input and check that, yes, with proper annotation, the end-to-end time to go from one sensor to one actuator is within the boundaries set by the system. This capability is the first stage to demonstrate that your system is conformant. As you may see from the results, the lowercase is valid, the uppercase is not, so you may still have some doubts. If you refine your system, you can say, okay, this is a set of threads inside my software elements. Therefore, I can go a little bit further and completely demonstrate that indeed my system is feasible, because some tools, like for instance Cheddar, which is embedded within AADL Inspector, will tell you that yes, indeed, your system is schedulable, all deadlines will be met, and the end-to-end flow latency is below a specific threshold that will guarantee that the controller of the UAV will fly correctly. So at this stage, we may consider that it's good news, the performance of the system is within the expected boundaries. We can go a little bit further and say, what if we want to do safety analysis? And for that, we'll use some specific tools within OSAT to perform FHA and FMEA analysis. And to do so, we will annotate the system with specific features, like for instance the propagation of errors from sources through component and ultimately to sync elements, so that you can perform an FHA analysis of your system, but also by combining more elements of your model, composite error behavior, for instance, ultimately build the complete fault tree of your system so that you can check under which condition your system may reach a failed state. And all those fault trees are built automatically from the architectural description, so that this architectural model is indeed the source of truth of your system. So as a conclusion, we see that through AADL, we can cover a lot of steps. We are not discussing model checking for the sake of time, but feel free to reach out to us if you are interested. And connections to systems engineering has already been covered by Adventium before during those days. So you see, AADL is a whole ecosystem that will allow you to combine a lot of analysis for the engineering of your system. As a conclusion, and obviously, it was just an overview of AADL capabilities. If you are interested, of course, you can reach to us and read more resources on the ACI AADL library and get more info on those elements. Thank you.
All right, John and Jerome, thank you very much for your recorded talks. We do have the pleasure of John being with us to help answer any questions you might have. I tried to tickle some questions from you. I haven't seen anything come through on the chat yet. So I'm going to start out with, I have an opportunity to ask some questions, and it reminds me of an old joke. A QA engineer walks into a bar, orders a beer, orders 0 beers, orders 99,999,199 beers, orders a lizard, orders 1 beers, and then orders a Shalikashvili. So with that as a kind of a run up to now, here comes a hard question. What do we got? John McGregor brings in a question. Oh no, I'm sorry, but it's by Cloud6, sorry. Could Alyssa languages be used for validation and verification? Hopefully I got that right. John, what do you think about that?
Yeah, absolutely. Within the Alyssa workbench, there are some languages, one language, AADL, to capture requirements. There's also a language verify, in which one can write the statements of what, how to do verification. Both of those languages capture properties and statements that are in AADL and feed the generation of the assurance case that Alyssa can generate. So yes, it can be integrated directly in the Alyssa workflow.
All right, thank you. Well, we wait for another question to come in. As I was listening to your talk, something crossed my mind. I want to not do it stump the chump here, but I actually do have a curiosity. As we think about model-based engineering, model-based systems engineering, and then digital twins, and how we manage to use those tools for putting software out to different end-use customers. I'm working on this one project where we have several different ships, and they all have slightly different hardware baselines, but we're pushing the same software to them. And that can be hard. So I'm wondering, how could AADL help us with putting product line software out to different, slightly different, but still different hardware deployments and still be safe and secure?
Yeah, that's a good point, good question. And it highlights one of the unique capabilities of AADL, because you're able to model hardware components, CPUs, memory, buses, and capture those properties that are particular to different types of hardware platforms. So for example, when you specify a processor, you can specify the execution speed, the clock of the CPU, which would affect the execution speed of any threads bound to it. So for each different processor that you want to model, you can in fact include properties for that particular type of hardware. And the neat thing about it is that whenever you bind software to that execution platform and run the analysis, excuse me, for example, latency, the change in clock speed would be reflected into the latency analysis. So if you bind the software to a processor that runs faster, you will get a noticeable change in the latency analysis results.
All right. Hey, thanks a lot for answering that question. It turns out that's just about all the time we have. So we have a short break before we get into the next talk. Thanks very much, John, for entertaining my question. And thanks for the one question we got from the audience. Appreciate your time.
Thank you.